So now let's plot the response of the parallel tuned circuit on a graph like we did with the series tuned circuit. Up the side we have increasing levels of volts that came through the parallel tuned circuit, and in the horizontal line we've got the frequencies that we used. And these frequencies were a little different because we were using an actual tuned circuit that was intended to be part of an aerial. So at the start we had a frequency of around about 10.7 megahertz, and that allowed 10 volts to come through. So let's put 10.7, we'll make a little marker there as to where it is, and a marker there as to where 13 is, and a marker there as to where 14.4 is. So here's 10.7, and it let the full 10 volts through. So that came up to there. And then we discovered by changing the frequency that there was a dip. There was a reduction in the amount of signal that came through, and at around about 13 megahertz only 6 volts got through, at max 6. And then at 14 or 14.4 and higher frequencies we found that the signal went back up again. Well, okay, it only went up to 9 volts this time, but it made a substantial increase. And if we join the dots together, we can see, go on then, that in this case, when the tuned circuit, the parallel tuned circuit, came to its resonant frequency, there was considerably less signal allowed to go through the parallel tuned circuit. And if we compare that to the series tuned circuit, which I just happen to have here, we can see it's almost exactly the opposite. So if a series tuned circuit is referred to as an acceptor circuit, it allows more of the frequency to go through when it's at its resonant frequency. A parallel tuned circuit is known as a rejector circuit. It only allows less signal to come through when it reaches its resonant frequency, and allows more signals to come through above and below its resonant frequency. So now we come to the matter of impedance. And to explain impedance, I thought I'd do it visually or pictorially rather than using just numbers to make it easier to understand. Here we have a part of a circuit which has a resistor, an inductor and a capacitor. Now the resistor may be a real resistor, or it may just be representing the total resistance of the wires in the circuit. But either way, there's a resistor here, and resistance isn't affected by frequency as the other components are. So I'm going to put a piece of card in here and tell you that by sitting the card on the bottom line here on the wire, this amount of resistance represents the value of the resistor and or the resistance in the wires. Now, impedance is frequency dependent, so we need to know what frequencies we'll be talking about, and in this instance alone, I'm going to say we'll imagine that there's a frequency of 7 megahertz travelling through this circuit. And we'll say that at 7 megahertz, the inductor produces that much inductive reactance. And it will produce that much capacitive reactance. Now we can see here that the amount of capacitive reactance is exactly the same as the inductive reactance at 7 megs. So one will cancel the other out, and the impedance of this circuit at 7 megs, when the inductive and capacitive reactances are equal, in other words at its resonant frequency, at this circuit's resonant frequency, the only impedance in the circuit is the amount of resistance that's left there. That's what happens at this particular circuit's resonant frequency, which I'm saying is 7 megahertz. So what happens if we reduce the frequency, if we send a lower frequency, let's say 4 megahertz of alternating current going through this circuit? Well, at 4 megahertz, the inductive reactance is lower. There's less inductive reactance. But as we've seen from the demonstrations, there will be more capacitive reactance. So what is the impedance of the circuit? Well, the impedance is the amount of inductive reactance subtracted from the capacitive reactance. So the impedance will be that much capacitive reactance and that much resistance. The resistance always stays. So the resistance and that much capacitive reactance will equal the impedance of this particular circuit at that particular frequency. Let's see what happens if we increase the frequency above that of the resonant frequency. The resonant frequency, you'll remember, is 7 megahertz. Suppose we put 10 megahertz into the circuit. 10 megahertz. Well, in that case, if we increase the frequency, the amount of inductive reactance will increase as well. And the amount of capacitive reactance will reduce. So how much is the impedance of this circuit? Well, the capacitive reactance will cancel out some of the greater amount of inductive reactance, and the impedance of the circuit will be the resistance and that much inductive reactance. I hope that's helped you to understand some of the significances of impedance. The actual formulas are quite complex, and I'm assured by the Irish Exam Board that they will not be, or the students will not be asked to actually work out mathematically what the impedances of any circuit are. So if you can just remember what you've seen here, that should help you to get an overall concept of impedance, resonant circuits, tuned circuits and resonant frequencies. I certainly hope so. So now we're going to show in simple terms what happens in a series tuned circuit. And on this graph, the signal strength is monitored in the vertical, minimum signal strength, maximum signal strength, and frequency is shown on the horizontal, low frequency here, high frequency here, and the resonant frequency of the tuned circuit is down this dotted line here. So with a series tuned circuit, what happened was that the signal wasn't allowed, or rather not very much signal came through when the frequency was lower than the resonant tuned circuit, than the resonant tuned frequency I should say. It was low, but as it got towards the resonant frequency, more and more the signal was allowed to go through, and then as it got higher, the frequency got higher than the resonant frequency, less came through. So at resonance, more of the signal, maximum signal strength, more of the signal came in, and at frequencies of below and above the resonant frequency, less signal was allowed to pass through. The series tuned circuit is often referred to as an acceptor circuit. Now let's see what happened with the parallel tuned circuit. When the frequency was below the resonant frequency, there was quite a lot of signal came through. But as we got close to the resonant frequency, less signal was allowed to come in until we got higher than the resonant frequency, in which case more signal came through. So with the parallel tuned circuit, you get less signal passing through it at resonance and more signal at higher or lower frequencies. Well, now we'll look at impedance. We haven't talked much about impedance in the video, but just to show you, impedance is measured in ohms, and it's denoted by the letter Z. and the impedance works in exactly the opposite way. So the impedance of a parallel tuned circuit at frequencies below its resonant frequency, it has a relatively low impedance, but the impedance increases the closer you get to that resonant frequency, and then it decreases, the impedance decreases as you get above the resonant frequency. So the impedance is inverse to the signal strength coming through. You get high impedance, which actually blocks the signal or reduces it greatly at resonance, and at frequencies above and below resonance the impedance is lower and therefore more signal can pass through. And if we look at the series tuned circuit, well, of course exactly the opposite is the case. The impedance starts high at frequencies below the resonant frequency and drops substantially at resonance, and then increases again when you get the other side, when you get a higher frequency than the resonant frequency. And so there you have it, series and parallel resonant frequency tuned circuits. I'm losing my words here, I'm forgetting the script. Okay. Impedance is high either side of the resonant frequency in a series tuned circuit, and the impedance is low either side of the resonant frequency in a parallel tuned circuit. Hopefully that's helped you understand a little more.